Okay, hello there, finite math students. I have not yet assigned your test on the first 3 chapters, but I have already assigned your next homework assignment, which I believe is due on October 26th. So you still have a lot of time. This is Wednesday, October the 7th, and the 26th is a little less than 3 weeks away. So three weeks from now, the date will be the 28th. So if the assignment is due on the 26th, that means you have 2 weeks and 5 days to work on it. And I think that's plenty of time. There really should be plenty of time. Okay. It's a large assignment that contains 141 problems. You know what, let me see if I can... hold on 1 second. There we go. Okay, it's a large assignment. It contains 141 problems. I realize that's a lot. However, there are many problems in Pearson's homework bank that I did not assign. I totally omitted them. So these are the problems that I think are the most helpful for you to do if you're going to really fully learn and master the material, okay? So again, I realize that some of you feel I assigned too much homework. 141 problems seems like a lot to do in 2 weeks and 5 days. However, some of the problems are actually extremely easy and you can do them in less than a minute. Furthermore, remember that you really are learning a lot of this material on your own. The best way to learn this material on your own is to just do a lot of problems. You need to go through a lot of these problems, struggle with them, and try to figure them out. That's the best way to learn the material. There's a lot of problems in Pearson's homework bank that I totally omitted. I did not assign them to you because I felt they were not absolutely necessary. The problems that I did include in the homework are problems that I believe are the most important for you to do if you are really going to learn this material and master it. Okay? Okay, so let's look at problem number 1. Excuse me. This is kind of bad English, I don't know who wrote this problem. Write the augmented matrix corresponding to the following system of linear equations. So we have 7x1 plus 3x2 plus 2x3 is equal to 1. We have negative 2x1 plus 8x2 minus 3x3 is equal to 6. Okay, let me expand this a little bit so you can see this better. Okay, the augmented matrix is, I'm just looking at the numerical coefficients. Okay, so in the x1 column we have 7, in the x2 column we have 3, in the x3 column we have 2, and then the constant 1. Okay, and then in the second row, first column, or the x1 column, we have negative 2, and then we have 8, and then we have negative 3, and then we have 6. And that should be the correct answer. Okay, so the first few questions are actually, pretty simple. So write the system of linear equations that is represented by the following augmented matrix. Assume that the variables are x1, x2, etc., etc. So here we have x subscript 1 minus 2 x subscript 2 is equal, that did not work. Okay, hold on 1 second. So subscript 2 is equal to 5. That should be correct. So this is like the opposite of the last problem. What equation corresponds to the second row of the matrix? 3x subscript 1 plus 7x subscript 2 is equal to 4. Okay, great. What equation corresponds to the third row of the matrix? Got to put my cursor in the box. Negative x 1 plus 6x 2. Oh, why do I keep doing that? Okay. Subscript 2 is equal to 5. And that should be correct. Okay, so this is just like the last problem. Okay. Yeah, if you hear my dog barking in the video, just ignore him. Okay, so this question 3 is just like question 2. Okay. Determine, so question 4 is really important. Determine if the following matrix is in reduced form. If not, indicate the row operation or row operations necessary to transform the matrix into reduced form. It is in reduced form. The matrix is in reduced form. Now the reason why is because look at the staircase of 1s. I have a diagonal of 1s that extend from the upper left, of the matrix going down. Look at the staircase of 1s. Every other number in the matrix is 0 except for the numbers in the very last column. So this matrix is in reduced form. So no row operations are necessary. The matrix is already in reduced form. Check answer, and that should be correct. Determine if the following matrix is in reduced form. If not, indicate the row operations necessary to transform the matrix into reduced form. Actually, ideally, this row, the last row, the bottom row of the matrix, should be switched with the top row of the matrix. I'm going to say the matrix is not really in reduced form, although this one's a little questionable. In my opinion, it is not. Pearson may not agree with me. Let's see. Okay, so Pearson does agree with me. Which row operation is necessary to transform the matrix into reduced form? We need to switch. Okay, we need to switch the first and the third matrices. We need to switch the first and the third rows of the matrix. We need to switch the first and the third rows of the matrix. Okay, let me show you how to do that in Mathematica, because that's important. You should know how to do that. So let's say I have this matrix. I'm going to call it matrix 0, 0, 0, 0, 0, 1, 2, 2, and 1, 0, 0, 3. Okay, I'll make it look nice, matrix form. And I want to switch the first and the third rows. So what I'm going to have to do is this. The first and the third rows, matrix 3, 1. And now let's see what the matrix looks like. Okay, now you can see the staircase of 1s that begins in the upper left of the table or the matrix. Here you have a 0, but you really want the number to be 1. Okay, so now this is in reduced form. This matrix is now in reduced form. Okay? Let's go to the next problem. Problem number 6. Determine if the following matrix is in reduced form. If not, indicate the row operation or operations necessary to transform the matrix into reduced form. So the matrix is not in reduced form. Why? Because of that 5. This 5 should be a 1. Okay, so the matrix is not in reduced form. Which row operation is necessary to transform the matrix into reduced form? Select the correct choice below and fill in the answer box within your choice. So what we have to do is multiply the second row by 1 over 5. And by doing that, it will change the 5 into a 1. The zeros remain 0. This becomes negative 2 over 5, which is the same as negative 0.4. Let's see if that's correct. How would I do that using the software that we're using for this class? Okay, so I'm going to clear the matrix. Let's start over. Matrix is equal to 1, 0, 0, 9, 0, 5, 0, negative 2. And I want it to look attractive. I want the output to be visually pleasing. Okay. So now I'm going to take the second row of the matrix and multiply it by 1 over 5. And I'm going to put 2 different commands on the same line. And if I do that in Mathematica, I need to use a semicolon to separate the two commands. Matrix, matrix form. There we go. And again, we can observe the diagonal of 1s, the staircase of 1s, which means that the matrix is in reduced form. Okay, so again, these are, this is just practice. This is practice. Let me see here. Okay, so these are problems that you can just do for practice. There's really okay, again, this is just more practice. So this is stuff that you should be able to do on your own. We can do problem 17, and problem 17 is very easy. It's very basic. Use row operations to change the matrix to reduced form. Clear matrix. Matrix is equal to 1, 2, 0. That's the first row, and the second row is 0, 1, 2. Okay, so this matrix is not in reduced form, because if this matrix was in reduced form, this number right here would be a 0. How do I make that number a 0? Okay. What if I take the first row minus 2 times the second row? Now, why am I doing that? 2 minus, what is 2 minus 2 times 1? Well, 2 minus 2 times 1 is 0. Okay, 2 minus 2 times 1 is 0. So if I do that, and then if I simply make that the new first row, then this element becomes 0. So 1 minus 2 times 0 is just 1. That's simple. 2 minus 2 times 1 is equal to 0. And then 0 minus 2 times 2 is going to be a negative 4. That number should be negative 4. all right? So matrix 1, because that's the row that's being changed, is equal to matrix 1 minus 2 times matrix 2. Matrix form. So we can see here that the second row isn't changed, the first row is changed. So 1 minus 2 times 0 is simply 1. 1 minus 2 times 0 is simply 1. 2 minus 2 times 1 is 0. 0 minus 2 times 2 is negative 4. That becomes the new first row. The second row has not been changed. So therefore, we will have 0, 0, negative 4, 0, negative 4, and 2. Okay, so there you have it. I mean, it's pretty simple. Question 18. Use row operations to change the matrix to reduced form. Okay, let's go through problem 18 step by step, because it is important. It's an easy problem, but you have to know how to do it. So clear my matrix, and let's start over. Matrix is equal to 1, 1, 1, 16, 3, 4, 6, 22. Okay, so remember, we want that staircase of 1. So we have a 1 in the upper left. This number 3 in the bottom column, this has to become a 0. So how do we do that? Well, what about if I take matrix 2, every number in row 2, every number in row 2 of the matrix minus 3 times every number in the first row, and that will become the new second row. So matrix 2, this is going to give me the second row of the matrix. Okay, matrix 2 is what I'm changing. This is going to be matrix 2 minus 3 times matrix 1. So it's the second row of the matrix that's equal to the second row of the matrix minus the 3 times the first row of the matrix. And what does that actually look like? It looks like this. Okay, so I have 1, 0, 1, 0, okay, so I have 1, 0 now. This one on top, this one that I've highlighted, this is in the first row, second column. That has to become a 0. So how are we going to do it? Matrix 1 is equal to matrix 1 minus matrix 2. Okay, so why am I taking the first row minus the second row, or why am I subtracting the second row from the first row? Because 1 minus 1 is 0. And then that number will become a 0. It's changed from a 1 to a 0. So then, let's see, matrix form. Okay, so now the matrix is in reduced form. 0, so I have the first column is 1, 0, the second column is 0, 1, and then I'm going to have negative 2, 3, 42, negative 26. And that should be the correct answer. Okay, there you go. Pretty easy, right? Let's see. Hold on one second. Okay, this is more practice, okay, one second. We're going to finish up with a word problem. Let's finish up with a word problem, because those are always a lot of fun, and we will use this method of Gauss-Jordan elimination to figure out the solution. Okay? I'm looking at question 45, and I will make other videos about this homework. I'm not done, but this will be the last problem for this particular video. The population of a certain country was approximately 50 million in 1900, 225 million in 1950, and 350 million in 2000. Construct a model for this data by finding a quadratic equation whose graph passes through the points 0, 50, 50, 225, and 100, 350. Use this model to estimate the population in 2050. Let x be the number of years since 1900 and y be the population in millions. This is a wonderful problem. So we're going to have 3 points. Point 1, now remember, x is the number of years since 1900, so we have point 1 is equal to 0, 50. So in 1900, x will be 50, and 50 doesn't mean there were 50 people in the country, it means 50 million people. And then point 2 is equal to 50, 225, and then point 3 is equal to 100, 350 million. Okay, so we have to set up a matrix. We're looking for a quadratic model. A quadratic model has the following form. A times x, well actually y. Y is equal to a times x squared plus b times x plus c, where a, b, and c are simply numerical constants. So we have to figure out the best quadratic model that actually represents that data. So to do that, we're going to use these x values and these y values, okay? So if you think about it, we know the x values and we know the y values. We're trying to figure out a and b and c. Alright? We're trying to figure out a and b and c, which are the numerical constants of the quadratic model. So in order to do that, let me see, we have, for the first row of the matrix, I'm going to clear the matrix, and my new matrix is going to look like this. Look at the point 0, 50. Look at the point 0, 50. Okay, so the coefficient of A is simply 0 squared, which is 0. The coefficient of B is simply 0. And then C we can represent with a coefficient of 1. The y value is 50, and that's the first row. Okay, now we're going to look at point 2. So the coefficient of A is going to be 50 squared. The coefficient of B is 50, and C is simply represented by the number 1, and then y is 225. Here we have, okay, I'm looking at the third point, so x is equal to 100. So the coefficient of A is 100 squared. The coefficient of B is 100. C is simply represented by the number 1, and y is 350. is my matrix. Matrix form. And now we have to solve it. Now, first of all, there's a 0 here in the upper left of the matrix. We want that to be the number 1. It can't be a 0. So why don't we switch the first and second rows of the matrix. So matrix, Matrix rows 1 and 2 will be switched with each other. It's 2, 1. Okay, so I simply switched the first 2 rows. Okay, now this has to be the number 1. How do I change 2500 into the number 1? I multiply by the reciprocal of 2500. So the first row of the matrix is going to be 1 over 2500 times the first row of the matrix. Let's see. Okay, so now I have the number 1. Below that I have 0, and then this is 10,000, but this column is not canonical. It will only be canonical when I have a 1 on top and all the other numbers in the column will be 0. So then matrix, the third row, is equal to matrix third row minus 10,000 times matrix first row. And okay, the first column is finished. I see 1, 0, 0. Okay, 1, 0, 0. Now in the second row, in the second column, there should be the number 1. I do not see the number 1. I see the number 0, and we cannot divide by 0. Okay, we cannot divide by 0. So I'm going to have to swap. I'm going to have to swap the second and third rows. So, hold on 1 second. Let me just erase. Let me erase this. Okay. Okay. Matrix form. Okay, terrific. So here in the second row, second column, I see the number 0. I want that number to be 1. If this number was, let's say, 4, I would divide by the reciprocal of 4. If the number was 12, right, I would not divide, multiply. I would multiply by the reciprocal of 12. If the number was 15, I would multiply the second row by the reciprocal of 15. 0 does not have a reciprocal, so I'm going to have to switch the second and the third rows. So matrix 2, 3, matrix 3, 2. Oh, hold on 1 second. Matrix form. Okay, there we go. So I switched the second and the third rows. This number here, well, this number here should be a 1. Oh, I'm sorry, that number should be a 0, but let's not worry about it yet. Let's create the 1. I have a negative 100. How do I change it into a 1? I multiply by the reciprocal of negative 100. Second row is equal to negative 1 divided by 100 times the second row, and the answer is... So now I see a 1 there. So below the 1 I have a 0. Above the 1 I do not have a 0, but this has to become a 0. So how do I do that? Well, I'm changing the first row. The first row minus 1 over 50 times the second row. Matrix form. Okay, so now we see that the first 2 columns of the matrix are in canonical form. The first column is 1, 0, 0. The second column is 0, 1, 0. I already have a 1 here in the third column, but these 2 other values have to become 0. So how do I do that? Well, let's change the first row first. So that's going to be matrix 1 plus 1 over 5,000 times matrix 3, and I'm referring to the third row because that has the canonical 1 in it. Matrix matrix form. We're almost finished. This value is 3 over 100. It really should be a 0. This number, 300ths, or 0.03, is in the second row. I'm changing the second row. So second row minus 3 over 100 times, which row has the 1 in it? It's the third row. Matrix form. There we go. Now the matrix is in reduced form, which means that these values right here are going to be the coefficients for my quadratic model. So I could do this. A, B, and C are equal to matrix, all the rows, the fourth column. So A is equal to negative 1 over 100, B is equal to 4, C is equal to 50. Okay. Use integers or decimals for any numbers in the expression. Oh, integers or decimals, so I think it doesn't want fractions, it wants decimals. Okay, negative 0.01 times x squared plus 4 times x plus 50. Okay, and that should be correct. According to the model, what will the population be in the year 2050? Okay, so let's figure this out. So, I'm going to define my function. Y is a function of x, negative 0.01 times x. Remember, in Mathematica, the space means times, to the power of 2 plus 4 times x plus 50. So we're starting with the year, okay, when did we start? Let x be the number of years since 1900. So we want the population in 2050. 2050 minus 1900, that's 60 years. Oh, wait a second. I'm sorry, not 1990, 1900. So the population of a certain country was approximately 50 million in 1900. I don't know why I was thinking 1990. Okay, so if it's 1990, it's 60 years, but yeah, 2050 minus 1900 is 150 years. So that means y 150, it should be 425 million. 425 million, and it should be correct. Let's see. Okay, so that wasn't too difficult, right? That was pretty straightforward. So we have 425. It is predicted that in the year 2050, the population in the country will be 425 million, assuming that we picked the correct model to represent the growth of the population for this particular country. Alright, there will be more videos to come. I hope this will give you guys a good start. And also, I will post your test. For the first 3 chapters, I will post your test in your Pearson course shell within the next few days. Okay, this is October 7th. So on October 9th or October 10th, I will have your test posted in your Pearson course shell. Okay, everyone, thanks and have a great week. Bye-bye.